So a couple of days ago, I got a new phone. I changed my old handy-dandy Nokia phone to the new iPhone 6. And one of the first things I wanted to do with it was to try out Siri, because I've heard so many good things about it. So the first thing I asked Siri was,
Siri not available. Connect to the internet.
Guess we'll have to connect first. Is it working now? Let's see. There you go. It should work now. So Siri, what's the weather like in Florida?
Here's the forecast for Tallahassee, Florida, the United States through December 12th, 2014.
That's pretty neat. I wonder if Siri can can play me a song on my playlist. Siri, play me Thinking Out Loud.
I couldn't find Hello I Would on your music.
We'll try once again. Siri, play me Thinking Out Loud.
Here's Thinking Out Loud.
When your legs don't work like they used to before, and I can't sweep you off.
Guess it works. I think I'm forgetting something tonight. Siri, tell me my schedule tonight.
You had 2 appointments at 6:30 p.m. At 6:30 p.m., Biopartnering seminar. At 6:30 p.m., BTC 1600.
Thank you, Siri. I should probably get on that.
Good evening, ladies and gentlemen. My name is Jeffrey Quesiga, and I am part of Team Symbiotech. Our members consist of James, Jonathan, Rachel, and Emily. Tonight, the topic of our talk is the future of speech recognition, an evolving conversation. Our agenda tonight is to go through an introduction and perspective on the technology, covering history and approaches to speech recognition. Following that, we will do a breakdown of speech recognition architecture, covering how speech recognition engines actually function and perform their task. Following that, we will go into current technologies used within speech recognition, and we will cover technologies such as hidden Markov models and neural networks, which you will hear about in a bit. Moving on, we will go deeper into neural networks to find out how they actually function and contribute to speech recognition success. And finally, we will cover commercial trends within the technology with a view to provide insights into the future of how the technology will develop. So our objective tonight is to predict the future of speech recognition technology and provide meaningful insights into the industry and where it is going. The scope of our presentation will cover the use of hidden Markov models and neural networks within the acoustic and language models of speech recognition. And finally, we hope to identify commercial and technological inflection points that will guide us to where this technology is going to go. From Apple to Google to Microsoft to Amazon, the tech industry is taking notice of speech recognition technology. Acquisitions of speech recognition technology and deep learning technologies are taking place with increasing frequency. But what are these technology giants madly rushing to acquire? What is it about speech recognition technology that makes it such an exciting buy for these multi-billion-dollar companies? Although our initial experiences with technologies like Siri are frustrating at worst and entertaining at best, companies are still investing heavy capital and large funds into developing speech recognition technology. So what is speech recognition, and what is its purpose? At its core, the purpose of speech recognition is to take to record human speech input and convert it into meaningful text output using computer-based algorithms. A simple purpose at first, and one that's easy to dismiss. But we need to look for the real value in this purpose, and that is through the intent. And the intent of speech recognition technology is to fundamentally change the user interface. Now that we understand the fundamental intent, we can see that the purpose of speech recognition technology is to bridge the gap between human beings and machines. Current methods of interacting with machines are, at best, outmoded and outdated. Taking the example of the modern keyboard, it's actually the descendant of the 18th century typewriter. But with recent advances in computing power, algorithms, we can actually formulate a new way to communicate with machines through the human voice. Applications in speech-to-text, such as voice command, text-to-dictation, and automated call centers are already in widespread use in mobile devices and many other fields. But why stop at just changing the input? Why not change the way we interact with machines entirely? The era of speech-to-speech communications promises to provide meaningful computer-human-based interaction through feedback systems such as smart homes, aircraft control systems with feedback capabilities, and personal assistants like Siri as they evolve. Now that we've defined the purpose and the intent, how do we actually approach the problem? That is, how do we get a machine to understand something as complex, varied, and intricate as the human language? There are three main approaches to speech recognition technology, the first of which is the acoustic phonetic approach. Now, this approach relies on finding and tagging meaningful references within human speech with phonetic markers, and then using these pre-tagged phonetic markers to identify future inputs of speech. However, this system is limited to words that it knows. If it has not encountered a word before, it will not recognize it. The next approach is the pattern recognition approach. Now, this circumvents the instance of not having encountered words before, because it makes use of pattern recognition, machine learning algorithms, and statistics to predict words based on identified features. So even if a system has not encountered a word before, it can actually predict what it is and identify it. And finally, we come to the last approach. This is the artificial intelligence approach, and this combines the acoustic phonetic approach and the abilities of pattern recognition with a knowledge-based system. And by knowledge-based system, I mean artificial intelligence. For example, IBM's Watson. These knowledge-based systems give speech recognition engines the power to infer meaning from speech inputs. That is, not just to recognize text, but to also understand what is in the text and being said. Now that we've defined how to approach the problem, what do we actually look for in human language to identify meaningful speech? Spoken language carries a lot of noise, not all of it meaningful. In fact, as human beings, we don't even speak in sentences. We speak in utterances. These can be a single word or a string of words put together to form a sentence. But what is it in these words that we look for? In this case, we look for the smallest meaningful unit that can give a change in meaning. In this case, a phoneme. And I'll walk you through a few examples of phonemes just now. Let's consider the words food and fad. Both of them are monosyllables, so we can't use syllables to actually locate them within a speech reference. And they both start and end with the same phonemes, F and D. However, if you look at the intervening letters, like U and A, you can recognize distinct sounds. And this is indicated by the distinct notation of the phonemes for U and A. Now, you may notice that these sound quite similar to vowels, and that's important. Let's look at another example. Hot and heat, another pair of monosyllable words. And they both start with the same phoneme and end with the same phoneme, H and T. If we look at hot, we can see the phoneme A, and if we look at heat, you can see the phoneme E. Now, these phonemes, as you've seen, are what give these words their distinctive features. And this is what a speech recognition system would look for. But where do these phonemes come from? How do we actually find them in human speech? Human speech is composed of vocal sound waves, and these sound waves are generated by vibrating vocal cords in the human larynx. These vibrating vocal cords produce a fundamental pitch in the human voice. Think of the fundamental pitch as the note you get when you blow into a recorder. Those things you played in elementary school, very squeaky, very loud. And this fundamental pitch is unshaped because it doesn't have any of the notes pressed on it yet. So keep that visual in mind as I go through. Now, the next point that I'm going to make is that sound waves have formant frequencies. And these formant frequencies correspond to specific shapes of the human vocal tract. So, for example, when I make the sound A or E, the position of my tongue changes, the rounding of my lips changes, and the position of my teeth also change as I open and close my jaw. Now, the important point here is that vowel sounds have formant frequencies, and it is these formant frequencies that we use to pick up phonemes. As I mentioned, the examples of A, E, and I. Now, I will hand it off to Emily to walk us through how these speech recognition engines actually pick up these phonemes and process human speech into meaningful digital text output.
Thank you, Jeff. So, I was excited about Rachel's new phone as well and decided to try it out for myself. So I asked Siri to please book me a meeting for 1 p.m. And it worked. But how is our message processed and then relayed as a string of words? More specifically, what is the process of speech recognition? We will refer to this process as the architecture of speech recognition and will be represented by these 4 interconnected steps. The first step is feature extraction, and it's used to isolate the voiced speech from the background noise and then to convert the sound into an appropriate form for computer processing. I will then discuss the acoustic model, which predicts the probability of a sequence of acoustic observations. The language model I will then discuss predicts a sequence of words. Lastly, I will touch on the decoder, a process whereby all of the predictions made by the language and acoustic models are considered and weighted, and then the decoder will make the final prediction as to what the observed output should be. Basically, it combines the predictions postulated by the language and acoustic models to predict what the machine quote-unquote heard, if it could hear. So I'll first consider feature extraction. So when you ask Siri a question, your voice is recorded. But not only is your voice recorded alone, so are the voices around you. The corresponding sound wave can be represented as a graph, whereby the x-axis is time in seconds and the y-axis is amplitude. The purple sound waves here represent the background noise, and the black sound waves represent the voiced speech. Theoretically, it should be possible to pick out voiced speech from this sound wave. However, due to the background noise, there's a lot of variability. So ultimately, feature extraction is used to reduce this voiced variability. That is, it picks out the fundamental formants that Jeff just spoke of. So let's use our example, Siri, please book me a meeting for 1 p.m. It will pick out the phonemes S, E, and E. It will then pick out the audio frames in time that correspond to these phonemes and then take the frequencies and convert them into an audio digital form that the computer system can then understand, extract meaning, and do further processing. So the next step in this processing system is called the acoustic and language models. The standard approach is to assume a probabilistic model, which we will take a look at now. W is equal to the predicted output given the observation X, and it is equal to the argument that maximizes W using P of W, which is the language model that predicts the sequence of words from the input, multiplied by P of X given W, which is the acoustic model, which predicts a sequence of acoustic observations. So it predicts the series of phonemic observations. So W equal to the arg max of P of W times P of X given W is the probabilistic model that combines predictions made by the acoustic and language models to predict an output of speech. So I will first consider the acoustic model. This model estimates the probability of a sequence of acoustic observations, such as phonemes. So let's go back to my meeting request. The acoustic model will predict the sequence of phonemes in a string of words. So for sake of ease, let's consider just the word Siri. The acoustic model will predict the probability of each phoneme, S, E, and E. The most pervasive approach to acoustic modeling uses probabilistic models to deal with uncertain or incomplete information, such as speaker variability. The most prevalent approaches used in speech recognition today are hidden Markov models, represented by this icon here, and neural networks, represented by the icon on my right. Both of these techniques will be covered in much greater detail later in this talk. So just to reiterate, P of X given W is the acoustic model, and it estimates the probability of a sequence of acoustic observations. We will now look at P of W, which is the language model. And again, this model predicts a sequence of words in a word string. That being said, the language model provides context to support the acoustic model and helps in distinguishing between sentences or utterances or even words that may sound very similar. For example, recognize speech versus recognize speech. The language model helps overcome this contextual mistake via the advent of a speech dictionary, which is a vocabulary that is trained on the speech recognition system, and probabilistic algorithms. The most prevalent algorithm used today for the language model is a model known as Ngram. So let's see how this works while considering my meeting request once more. How does the speech recognition system calculate the probability of this sequence of words specifically being observed? It does so using the Ngram algorithm. Ngram is based on the assumption that the next word in a sequence is dependent on the word preceding it. In other words, the model considers the probability of W being observed given the word before it, so W before. So, what is the probability of the sequence of words, Siri, please book me a meeting for 1 p.m. being observed? For sake of ease, let's only consider the 3-word sequence, book a meeting. And in this example, we will pretend that there's no word coming before book and no word following meeting. So the system breaks down this this sequence into 2 components. So the probability of book a meeting being observed in that order is equal to the probability of book being the first word in the sequence multiplied by the probability of A following book multiplied by the probability of meeting following A multiplied by the probability of meeting being the last word in that sequence. So when you multiply all these probabilities together, you end up getting the overall probability of the sequence book a meeting being observed in that exact order. A current advancement in relation to the language model is a technique called natural language processing. This concept can be considered an intersection between artificial intelligence and linguistics, whereby its role is to ultimately extract meaning from text through syntax and semantics. According to speech recognition, natural language is considered more conversational or more spontaneous, which is much less formal than the way I'm speaking here before you tonight. It may include stutters, ums, or ahs. One way of improving speech recognition technology is to break down larger words into more, subcategorized forms, which is known as subcategorization. And this involves breaking down the word into its prefix, root word, and suffix. Another way of overcoming a speech recognition process's ability to form natural language or process natural language is through adding additional rules or constraints. For example, the word buy only refers to the verb to make a purchase. Through improvements in natural language processing, the recognition system will be better able to understand context-dependent situations, including intonation, and ultimately extract meaning. So at this point, we've extracted the phonetic features from a speech output and then converted them into an appropriate form for further processing. We then consulted the language and acoustic models to predict the word sequence of maximum likelihood. The last step in speech recognition is the decoder. The decoder is used to make the final prediction of an observed sequence of words. It does so by combining the predictions made by the acoustic and language models in the form of its maximum likelihood. So if we have an input sequence and its phonetic features are extracted and then fed through the acoustic and language models, the models will predict and identify separate features pertaining to different characteristics of the input. So for example, in this case, the acoustic model predicted that the output does not have edges, so it predicts circles of various colors. The language model predicts that the output is pink, and therefore predicts that the output may be pink circles, squares, or triangles. What the decoder does is combine these predictions and makes the final decision, whereby it chooses the pink circle, and an output is produced. This entire process is known as the speech recognition process, and this is how Siri processed my request. I will now pass it off to John, who will be discussing common techniques of the acoustic model for speech recognition processing.
So as Emily mentioned, I'll be going over hidden Markov models and neural networks, which are machine learning algorithms that make up acoustic modeling and speech recognition. But first, let's look at a quick timeline of machine learning and speech recognition technology. Hidden Markov models were invented in 1970 by Larry Baum, and he shared it with many advanced research project agency contractors, including IBM at the time. However, it was not until the late 1980s and especially the 1990s that hidden Markov models were being widely used for commercial speech recognition systems. They are still being used today, however, they're dying out, the reasons for which will be covered later. Now let's say I ask Siri a simple question, like, how do I grow a tomato garden? How does Siri break the words in this sentence down? As an example, how does Siri recognize the word tomato? Well, what the system does is recognize the individual phonemes of the word using a machine learning technique known as a hidden Markov model. So what is a hidden Markov model? A hidden Markov model, or HMM, is a graphical modeling tool used to represent probability distributions over sequences of observations. Over the last 25 years, it has been the most popular method for acoustic modeling in modern general-purpose speech recognition. There are four main components that make up an HMM. It consists of a random variable that changes over time to represent the state of the system, shown here in the blue box. In the HMM architecture, the state is only partially observable. In other words, it is hidden, which is how the HMM gets its name. The state is influenced by a CPT, or conditioned probability table, which is a distribution of probabilities that can influence it. The model also uses observations, shown in the purple boxes, to infer the state of the system at any given time. There are two important properties associated with HMMs that I should mention. First is the hidden Markov process, which says that the future state depends on the past states through the present state at time t. In other words, the next state in the model depends on what the current state is, which is influenced by the state before that, which is influenced by the state before that, and so on. The second property is that the current observation is independent of all other observations. So let's apply this architecture to speech. As mentioned earlier, when you speak into a microphone, the microphone registers sound waves and converts them into digital signals depending on their amplitude. These are then further broken down into even smaller acoustic sound waves, also known as acoustic sound vectors. In acoustic modeling, we may think of an acoustic sound wave that is picked up by a microphone as the observation, and we may think of the phoneme that the HMM infers based on the sound vector as the state of the system. Furthermore, the model infers what the current phoneme will be based on the previous phoneme, a characteristic of HMMs. So there's a hidden state for each phoneme in each word, and this model can be scaled up to have hidden states for whole words using the previous words to make predictions for the current word. So just to review hidden Markov models, an HMM is a stochastic graphical modeling tool that is used to generate outputs based on changing observations over time. There are four main components: the hidden state, which is influenced by the external observation, a probability distribution, and the previous state. Or, if we apply this to speech, these would be the phoneme, influenced by the acoustic sound wave observed, a probability distribution, and the previous phoneme. Now let's return to our example of breaking the word tomato down using a hidden Markov model. The model starts by observing the acoustic vector for the letter T, followed by another acoustic vector representing a vowel sound. It uses the observation, which is the acoustic vector, the previous letter T, and the probability distribution that it has been conditioned to determine the phoneme. In this case, it goes with the O phoneme. The model then observes an acoustic vector representing the letter M, and this is followed by another acoustic vector representing either A or A. And again, it uses the probability distributions, the observation, and the previous state in the model to make a decision on this state. It then does the same process for the final phonemes of T and O to get the word tomato. This is an extremely simplified version of how the model works, but it gives you a better idea. Now, as I mentioned, hidden Markov models have been very popular in the past and continue to be popular on a commercial level for acoustic modeling in speech recognition. There are a few reasons for this. The first is that speech can be thought of as a sequence of discrete stationary signals that change over time. HMMs are designed to track temporal changes in variables over time and infer an output based on an external observation and the previous outputs. Second, HMMs are easy to train. For speech recognition, they can be trained, meaning the probability distributions associated with certain states can be set using the dictionary of whatever language you're training the model in. And finally, they're fairly simple to build and do not require much computational power compared to other speech recognition models. However, HMMs are not perfect, which is one of the reasons they are beginning to die out. The first drawback is that the model collapses under the weight of large amounts of data. If we have a lot of information going from the first half of a phrase of speech to the second half, the model starts to break down and it doesn't perform very well. The second drawback is that HMMs do not provide much insight into the recognition process, and thus it is difficult to analyze the errors of an HMM system in order to improve future performance. So now that we've gone over what has traditionally been one of the most popular machine learning techniques, let's move on to what has become the most exciting and promising advancement in the last few years, neural networks. Originally, computer scientists sought to emulate the brain in terms of processing information and carrying out functions. The approach to neural networks was inspired by the biology of human neurons and their connections. However, modern implementations of neural networks have evolved from what they were originally and have taken a more practical approach based on statistics and signal processing. Today, neural networks are used to approximate functions that can depend on a large number of inputs and are generally unknown. Once again, let's go back to our timeline of speech recognition technology. In 1958, Frank Rosenblatt created the first generation of neural networks, known as the perceptron. However, these were very limited in their use. In 1985, the second generation of neural networks came about, which used a method known as backpropagation to train them. But these didn't work very well for a few reasons, these being a lack of labeled data, low computing power, and a failure to understand how to initialize the networks properly. In 2006, Dr. Jeffrey Hinton's lab at University of Toronto made strides in the field of machine learning with the creation of deep neural networks, which consist of many trained layers. And over the last couple of years, recurrent neural networks have begun to gain momentum as a way to do acoustic modeling in speech recognition, and these are seen as the method of the future. Neural networks have had a very unconventional life cycle as a technology. Normally, a technology is invented, it rises in popularity, and then it dies as a better technology comes along and replaces it. However, neural networks first came about in the late 50s and early 60s, but in the late 60s there was a famous paper that came out that denounced its application to machine learning. It was a long time before they received any attention again, but they became fairly popular in the late 1980s with the invention of backpropagation, but fell out of favor in the 90s for speech recognition and were replaced by HMMs. In the last 10 years or so, however, they've made a resurgence as deep neural networks have been found to be very appropriate for speech recognition technology. So as I mentioned, neural networks are inspired by biological neural systems, and they have similar parts. An artificial network consists of nodes with connections between them, similar to neurons and dendrites in the brain. To get the network to do something, we trigger a node with an input, and that in turn triggers the nodes it is connected to. This is comparable to firing a neuron and getting an action as a result. We organize the nets in a way that gets results, with directed connections to accurately follow the flow of information, differently weighted connections to represent different values placed on various connections. And this is how learning occurs, with repeated inputs to the same neuron or node over time to cause a greater likelihood of that node causing an action in the future. And we also have well-defined input and output nodes. We have an analogy that may help you understand how a basic neural network works. It's based on a TV show that many of you have probably seen, House. If we compare how House operates in the hospital with neural nets, it's fairly similar. House is the main doctor in the hospital, and he has other doctors working for him who provide suggestions about a patient's condition. In this situation, the patient who comes into the hospital represents the input, the doctors working for House represent a layer of nodes, and House is the output, giving a diagnosis. The patient gives the doctors information about how they're feeling, they make an assessment, and relay their opinions along to House, who then gives an output based on the information given to him. Based on the performance of his doctors or how often they are correct, he may come to trust some more than others with their opinions. This is equivalent to changing the weights of connections in neural networks or relying on some nodes more than others for an accurate output. Now let's look at a simplified depiction of the architecture of a neural network. The network consists of various input nodes that make up the input layer and various output nodes that make up the output layer. However, we also have another layer of nodes, the hidden layer, which creates more connections within the network. Each node in the hidden layer is also given a transfer function to judge its inputs and decide if it wants to pass them through to the next layer. Furthermore, this is a feed-forward network, meaning the inputs can only go one direction through the network, forward, as shown here. Now, I mentioned earlier that the connections between the nodes were weighted. This setting of weights must be done when the system is created. The weights determine the path that the inputs will have the greatest effect on, as shown here. Often, these initialized weights do not produce ideal outputs from the inputs. So the network has to learn, via training, what weights to have on its connections in order to produce desired outputs. A very popular method for doing this is via backpropagation, which I'll demonstrate. We start with initialized weights, and then for a given set of inputs, we decide on desired outputs. We let the network generate outputs based on the initialized connections, and then compare the calculated outputs to get what's known as the error in the network. We use the error to alter the weights of connections to get closer to the desired output. This adjustment flows back through the system until all the weights are adjusted, and we run the network again. We continue this process until the calculated output is equal to the desired output, and we repeat this for each input set. So that's an introduction to neural networks, and now James will describe some of the more complex forms that are being used for acoustic modeling in speech recognition today.
So although neural networks were originally designed and inspired by biology, as they become more complex, they've evolved to incorporate a more practical approach based on statistics and signal processing. So to start off, here are the very basic components of a neural network. You have your input, your hidden layer, and your output. But to better visualize a deep neural network, we need to add more layers. And in reality, this is still a really simplistic portrayal of something that's normally very complicated. So complicated that's usually referred to as a black box because we can't really tell how an input really turns into the output that we're given. So What we usually do instead then is use something called credit assignment paths. And these assign credit to any sort of potential path that the input may take to become the output. As mentioned before, original deep neural networks are feed forward. That is, all the input information only flows forward through the network from one layer to the downstream layers only. But the main use we've gotten out of deep neural networks is known as the hierarchical abstraction of information, and that is, as information flows through the network, we're able to recognize patterns by first recognizing really general, simple patterns, and then building off of those patterns sequentially to more and more specific patterns. So to explain that a little better, we can go back to the analogy we use with the patient and Dr. House. So that would be the patient is the input feeding information to the network, and the network itself is represented by the hospital. So it first identifies a really simple pattern. Maybe it notices that the patient is injured. It's very general, and there's no specific information we can really get out of that. But using that pattern, the network can find more specific patterns. If it knows that it's injured, it might easily figure out that the patient has an injured leg. Using that pattern, we can find even more specific patterns. Maybe the injured patient's leg has a broken bone. So this shows the purpose of a deep neural network to identify very specific patterns by continuously building on more generic patterns. You have your injury, which is very general. You have your injured leg, which is more specific. And finally, you have your injured leg bone, which is the most specific. So that, again, is by sequentially identifying more and more specific patterns from general ones. So deep neural networks were a start, but since then, we've added a lot more improvements and advancements to get more use out of them and new features. So this brings forward recurrent neural networks and recurrent architecture. It's still really similar to the original architecture I just talked about, in that it has an input, it has your hidden layers, and it has an output. But the difference here is that in recurrent neural networks, the information flow can go both forward, as in feed-forward networks, and sideways, or even potentially from a node to itself. So this allows you to have more connections using the same number of layers and the same number of nodes, which in turn gives a network both more power and more biological similarity. This is through sequential and parallel processing of information. So the type of recurrent neural network I'm going to talk about tonight is known as long short-term memory, which uses something known as LSTM blocks that contain 3 gate cells and a memory cell as shown in light green. So for long short-term memory, each block, and there could be many in a network, is sort of like an additional smaller network within that network. And it's designed specifically to remember information and not just weights. So within the LSTM block, you have 3 gates. The one on the right is the first gate. It's known as the write gate. It decides which information is relevant to store, and if it deems that information to be relevant, it stores it, it allows it through, and stores it in the memory cell. The next gate on the right is known as the read gate. If it thinks this information stored in the memory cell is relevant, it opens up and allows that information to be read from the memory and go back into the network. The last gate on top is known as the keep gate. This gate's purpose is to allow new information to flow into the memory cell and erase what's in the memory cell if it thinks it can store something better. That's seen there. So how does the long short-term memory in recurrent neural networks and this architecture in general compare to the original first deep neural networks? So we can compare the two with a few easy, simple characteristics. And first of all, we're going to look at biological similarity, because better similarity to biological networks can help us better understand how the brain functions. With deep neural networks, traditionally, they only feed forward, whereas recurrent neural networks can allow more connections between layers, which is better representative of how the brain works. These additional layers, as we established, can give a sense of time and more context. Deep neural networks can't use this. But commercially, despite the advantages shown here of recurrent neural networks, deep neural networks are the gold standard. There's still room for improvement, but compared to recurrent neural networks, which haven't been optimized for speech recognition technology, deep neural networks are still the preferred choice. So last point here I want to highlight is the use of all temporal time. Deep neural networks have no sense of time, but recurrent neural networks have a little bit in that they can identify current information, that which is being fed through the network now, from past historical information, for example, stored in the memory cell. But what if a network could use all the information, all the temporal information in the input, and use that to predict the best output? And that brings us to the current state of the art. So this may seem like a lot in that it's deep, bidirectional, long short-term memory, recurrent neural networks. But this is really just building on and combining a lot of the concepts we've already talked about. These are deep neural networks in the sense that they have multiple layers for hierarchical feature abstraction. The new part here comes from the fact that these networks are bidirectional, which means you can process a signal in two completely independent, separate hidden layers at the same time, and then provide the same output to the next layer. So an easy way for us to actually picture this is imagine the network reading a sentence from beginning to end, and then end to the beginning at the exact same time to best understand the sequence of words. Again, these networks, hence long short-term memory, they make use of the LSTM block, which can store information in the memory cell. And these are also recurrent neural networks, which means they can have the connections within a layer or even within a node to itself for more processing power. So we can compare these new state-of-the-art networks to the original chart we had before. And many of these are going to be similar because, again, these are recurrent neural networks. But the difference here comes from the fact that these new state-of-the-art networks have shown the best recorded accuracy in standard industry speech recognition tests, making them really promising for the application in industry. And going back to the last point I mentioned in that the use of all temporal time, these networks use all available temporal information, that is reading the sequence, the input from beginning to end and end to beginning at the same time to make the best possible prediction of what the words might be. So to summarize all the technology we've talked about that's included in the acoustic layer, we began with hidden Markov models, which used some kind of observation, like the sound wave, to infer a hidden state, that being the phoneme. We've looked at deep neural networks, which used hierarchical feature abstraction to build on really general patterns, sequentially identifying more and more and more specific patterns from that. And we've looked at recurrent neural networks, specifically long short-term memory, which use the three gates, the write gate to decide which information should be passed on to the memory cell, the read gate to decide when that information should be passed from the memory cell back into the network, and the keep gate to rewrite that information when new, more important information is available. So how do these technologies and advances in these technologies actually translate to observations commercially? And that's what we're going to discuss next.
Thank you, James. So now that we have looked at the technology behind speech recognition extensively, we can now take a look at what is being used in today's commercial platforms. So most speech recognition system needs to use the cloud for optimal conditions. And what I mean by that is that they need to send the input they get, the audio input they get from the microphone to the cloud, and it will get processed and sent back to the phone after it gets processed. So now let's talk about Google Now. Google Now is Google's speech recognition platform, and it was developed in-house and currently uses deep neural network as its architecture. Furthermore, it also uses Google's other platforms, such as its search engines and map services, to boost its capabilities. Earlier this year, Microsoft released Cortana. And Cortana was also developed in-house and also uses deep neural network as its architecture. And it is said to boast the capability of tailoring the system to your habits, such as your sleeping habits, so it will set the alarm according to your normal day-to-day activities. And lastly is the platform on my new phone. So Apple is an interesting case because it licenses the technology from a company called Nuance. They did not develop this themselves, and up until this day, it still uses the hidden Markov model as its architecture. And this is why Siri is usually less accurate compared to Google Now. So you might be wondering what happened in the market to bring all of these commercial platforms in place. Well, one way we can look at this is to look at the recent mergers and acquisition trends that have been going on in the past couple of years. As Jeff mentioned earlier, A lot of the blue chip companies are investing in not only speech recognition companies, but also neural network companies over the last couple of years. In 2010, Apple bought Siri International, which was a spin-off from a military project, and used the virtual assistant platform from that company in conjunction with the technology from Nuance for the release of Siri in 2011. And as I mentioned earlier, Apple does not have its own speech recognition technology platform. So in 2013, they acquired Novaris and Q to help them develop their own platform, presumably using neural networks. Google is also jumping on the bandwagon, as they have recently made 2 acquisitions in the last couple of years. The first one being DNN Research, which was a spin-off company from Dr. Hinton's lab here at U of T, and that was bought for $5 million. And the next acquisition is the acquisition of DeepMind Technologies, which is a neural network and machine learning company, and that was bought by Google for $400 million. So you can see that the technology is going places as the industry is increasing its investment in this field. So now that we know the technology is picking up, we need to know where we are at in terms of its inflection points before we can forecast the technology. And there are 2 different inflection points that we can talk about, the first being the technological inflection point, and the other one being the commercial inflection point. So here we will discuss the technological inflection point first. So here we are at 2014. Where are we at in terms of the inflection point? Well, experts argued that we have passed it in 2006 with the use of deep neural network as applied to in speech recognition. And the current standard metric for speech recognition is the word error rate, by which they measure the number of words the system gets wrong as an overall percentage. And with deep neural networks, we were able to achieve a 25% decrease in word error rate. And what I mean by technological inflection point is that we have moved from using hidden Markov models to deep neural networks in today's commercial platforms. And as James mentioned earlier, we also have recurrent neural networks and deep bidirectional long short-term memory recurrent neural networks. And we can regard these as incremental advancements in the technology that will help us reach the 0% word error rate eventually. So now where are we at in terms of commercial inflection point? Well, experts argue that we have not currently passed the commercial inflection point yet. And what I mean by commercial inflection point is the point of mass adoption. And I'm not talking about an absolute user number, but I'm talking about the point where the technology becomes seamlessly integrated into our everyday lives. And there are still many factors that need to be overcome before we can reach this point. And the first point is multimodality. And multimodality refers to the combination of speech recognition technology with other forms of pattern recognition, such as facial recognition or gesture recognition. And with this, you can have a more robust recognition system where the output from one system can reinforce the output from another, giving you an overall output with a higher confidence level. Take Siri, for example. Siri can use GPS location in conjunction with the speech command. So let's say, for example, you're planning to go to London and you ask Siri for restaurant suggestions. And it might give you restaurant suggestions for London, England, or you're only actually going to London, Ontario. So you can see that combining speech recognition with other forms of pattern recognition can really help expand its uses. The next point is emotion recognition. Emotion in speech is extremely important as it contributes to our overall meaning and context of what we are saying. And this ties back to the natural language processing that Emily mentioned earlier. And currently, we are able to detect emotions by detecting variations in pitch, duration, or vocal tone, but these are not yet commercially available. The next point is the user interface. Now, systems such as speech recognition technology need to be optimally designed for its end users for it to add a great value for the users. And take Siri, for example. Siri cannot be used in conjunction with other applications currently. So what I mean by that is that when you use Siri and a phone call comes in, Siri cannot stay in the background and it will automatically quit. So having a more optimized user interface system for Siri, we can imagine it becoming more useful for us as it will become more of an assistant if it stays in the background of our phone. Most systems currently use what's called a supervised learning. And supervised learning is where you have the machine produce its output, and you can tell it if it made the wrong or the correct answer. And if it made the wrong answer, you will then need to tell it the right answer for it to learn. And this is currently commercially feasible because of the amount of labeled data we have. But in the long term, we expect unsupervised learning to be a solution for these machine learning algorithms. And with that, the machine can learn by itself, and we will not need to label the data that we use, and we can also take advantage of the big data that's coming in the near future. And the last point is productivity. Currently, the standard metric for speech recognition, as I mentioned earlier, is the word error rate. But we feel that as it becomes integrated into our everyday lives, we need to look at it in terms of the productivity that it adds to our everyday lives. So let's take Siri again as an example. You can ask Siri to draft an email for you today, but you will still need to go back to it to correct the grammar and the punctuation. And this doesn't really save you time or add productivity to your life, because it takes the same time as you would have if you did it yourself. So we can imagine a time where we can measure Siri in terms of the productivity that it adds to our lives, where we can trust Siri to send an email for us with the correct grammar and punctuation, so that not only that it saves you time, but it also adds productivity. As a final point, all of these points will need to reinforce and help each other as we reach the commercial inflection point. And even if the commercial inflection point is still a long way away, we can still see some commercial translation from improvements in these 5 areas. So what should we be looking out for? One possible application is machine translation. And what I mean by machine translation is having your speech recognition system take the input from one language into another language with the same meaning. And here you can see that emotion recognition can come into play, because emotion is important in terms of context and meaning. And here also, the point of productivity is also important, because even if the word error rate is not perfect, as long as it can translate your input with the same meaning, you can imagine that it will add productivity. And one example of this is Microsoft Skype Translate, which is supposedly able to translate in real time one language to another over Skype. Now, there are currently many speech recognition technologies that are available, and one example is a smart home device. And the idea behind smart home is to be able to control your home environment automatically by voice. But currently, it can't really do much more than what you can do on your phone, so it does not add significant value. But if you segment the market and find a demographic that can use it properly, it will be a step forward. And one such example is aging at home, where the smart home device can help the elderly to live independently for a longer period of time, as it can assist them for their day-to-day activities. And one such example is the device called Coach, that uses a voice and speech input for fall detection. So you can still see here that productivity comes into play, and also multimodality and emotion recognition. As James mentioned earlier, there is a lot of movements or advancements in the industry, and this will obviously translate into commercially in the near future, but some of these may not be visible to the consumer market. And one such example is the replacement of deep neural network and hidden Markov models, replacing the current into recurrent neural networks and subsequent architectures. And this will happen because it will add accuracy and also power to the speech recognition systems that we have today. So your iPhone 7, 8, 9, or 10 will have a smarter Siri and should not give you Google searches for answers. And the last possible application is speech recognition in wearables. And commercial wearables is an increasing trend in the industry. And with this, you can see where the problem of user interface comes into play. You wouldn't want to type an email on your Apple Watch because the screen size is too small. So you can see that you are limited in the ways that you can interact with your wearable device. And furthermore, you can see that speech recognition can add productivity value to this technology. And with most wearables, you can detect a lot of parameters, such as your heart rate measurements. And this also comes into play with multimodality. As you can imagine, that it will add to the usefulness of the product Take, for example, emotion recognition. The acoustic cues that we find from speech can distinguish between anger and happiness. Cannot really do it very well because the acoustic cues is very similar. So, for example, we have a high pitch and a high duration. But you can imagine that with your heart rate measurements, it can definitely contribute to the emotion recognition output at the end. So even if the commercial inflection point is still a long way away, we feel that there will be still commercial applications that will come out from speech recognition technology. So as a conclusion, speech is one of our more natural ways of communication. And the premise behind speech recognition was first to transcribe speech to text, but now we are seeking a more natural way of human-computer interaction. And in speech recognition system, both the language and the acoustic models contribute to the final output. And through advancements in both the acoustic model, the language model with natural language processing, and the acoustic model with neural networks, we have passed the technological inflection point, but we are also getting closer to the commercial inflection point that I just mentioned before. We are looking forward to seeing this technology becoming an integral part of our lives where we believe that it will add significant value. Thank you.
Great presentation, guys. I learned a lot. So my first question is, you only explained acoustic model and language model in English. Have you guys considered about other languages? Because they have different structures and they have different inputs. So do they have to use another layer of algorithm to process it, or use the same one, just add more time?
So to date, a lot of the literature actually comes from places like India and China. So I would assume that they do have processes there. However, I'm not 100% sure. So quite honestly, I can't answer your question for certain. So all of our research focused on the English language. For example, we spoke to people with IBM Watson, and one of the fallbacks there actually was that they've only developed this program or this system in the English language. So that's one of the fallbacks there.
Thank you. So for page 50 on your slides, yeah, I'm just wondering the inflection point. So where do you guys got information from?
So in doing this, we spoke with a lot of people who just work in the industry. And a lot of this is just speculation and opinion because it's all forecasting. So there's not a lot of definitive time periods. But we talked with a lot of people, and although their opinions were different in different ways, for the most part, they recognize that it will still be a while, but this is still feasible to see stuff like this within the next 10 to 20 years.
Thank you.
Great presentation, everyone. So in doing your research, did you come across any trends or compare the adoption perhaps in different areas? Is there anything faster growing, slower growing? What do you think in your forecasts, you've presented several possibilities. What as a group do you think is the highest potential?
Sorry, so when you say what trends do we see, do you mean outside of speech recognition or just outside of these applications we've mentioned?
Within the applications. So have there been any that have been taken up much faster than others in different areas of technology, I suppose?
We haven't looked directly at a lot of the commercial applications. We focused more on a conceptual approach, so that was the multimodality, unsupervised learning, emotion recognition, and productivity and all those. And the commercial forecasts we gave were just potential situations for actual so that we could observe in the market developments and actual applications for those conceptual frameworks before. What we've seen, what we have data for is mostly with like smartphones, personal handheld devices. So we found some adoption rates with smartphone technology, and that's really commercially to the general public where a lot of us see this technology. So that's been the center of its growth.
Okay. Great work, guys. I just have a quick question. So you mentioned the last speaker, you talked about Skype and its ability to translate in real time, but you said it with some chagrin. Did you guys actually try the Skype translation program, and did you actually have any success with it?
We didn't try it. You have to register for those.
Oh,
so
okay.
I don't know if you have to pay or not to try
All
them. I would imagine not, but we didn't try it. It's not released yet.
All right, commercial inflection point. Okay, people need to actually pay for it. That's fine. So on slide 52, when you were talking about what sort of factors can help speech recognition technology reach the commercial inflection point, you talked about unsupervised learning. Could you, maybe I missed something, could you quickly talk about what that is again? I mean, from what I understand, it means my smartphone is listening to me all the time, every day, even when it's in my pocket. Is that incorrect? Please say it isn't, because it sounds terrifying.
No, that's not true. Siri
Good.
only listens to you if you open it.
Right.
So if it doesn't, then it won't listen to you. Don't worry about that. But unsupervised learning here refers to more of the machine learning algorithms. So with supervised learning, you kind of have to teach it. So for example, if the neural networks comes up with a word that's wrong, you have to tell it that it's wrong, and you have to give it the right answer. But with unsupervised learning, you just kind of let the system figure it out by itself, and it will eventually, hopefully, get the right answer throughout its multiple processing times.
So how does that work? Do you have any idea? Or those are
Okay, so when we talk about unsupervised learning, we actually talk about letting the system learn by observation and actually extract features of meaning by looking at the data it has as a whole, and then learning how to pick out patterns by itself. An example of this would be one of DARPA's challenges to create a driverless vehicle. They initially had some successes and some failures in the Mojave Desert by having all of these competitors design these driverless vehicles. And this is a form of unsupervised learning, and it doesn't involve reward for the system. So this is called reinforcement learning. Basically, the system drives toward a goal, and based on how close it gets to the goal, it can push harder or further. And that's my understanding of it at best. And this is one of the reasons why speech recognition technology is a little limited, because it can't always use unsupervised learning. A lot of what we have now is based on supervised learning because there's more labeled data, and it's more commercially feasible for companies to actually do this.
okay. Thank you.
So my question is, what does the patent landscape look like in this market? And how does that affect technology development?
The patents? There's a lot of patents involved. If you're, Well, as I mentioned earlier, Nuance, the company who licenses the technology for Siri, they have a lot of patents on speech recognition. And one problem with them was that their patent was kind of broad. So there are a lot of startups that came up with speech recognition technology ideas, but all of them could not commercialize their idea because Nuance's patent was so broad. So Nuance basically acquired all of them. It's one of the big companies in speech recognition.
I'm just wondering, for the speech recognition, so you guys only mentioned one possible way is to implement on the smartphone. have you guys considered to apply this to other like devices, such as automobile televisions?
So we focused here on smartphones because it's probably the easiest to relate to. But in terms of other applications, a lot of speech recognition technology, specifically like Google's platform, I believe they have an SDK for it if you want to use that as an input for your other devices. So if somebody wanted to come up with, like, say, a TV or something else that uses speech recognition, it wouldn't be that difficult for them to actually implement that, but it wouldn't really change the fundamentals of how the speech technology platform works. It's just finding other applications for it.
To build on Jade's question, so if I'm a startup and I want to build and design TVs that capture my voice commands, that means I have to pay like a license to Google to use their voice recognition software. Is that correct? Okay, good. So that builds into the commercial inflection point. Interesting. Okay, we're done.
So it's a different topic tonight, guys, so I'm not expecting a lot of questions, but are there questions from the broader audience? Oh, maybe there are a few questions.
Hey, guys. Sorry. Go ahead. Oh, just one question. So, great talk on interesting technology. Since you mentioned there was a forecast-to-go of it, I'm a greedy guy and I'm interested in the stock market. So I was wondering if you can comment on how the stock prices for these companies with these technologies have changed over the past few years and how that might compare to an other industry which is, I believe, still growing, such as the biotech industry, over companies such as Gilead.
So we haven't looked into stock prices for any specific companies in this industry, but as we mentioned with the acquisition of DeepMind, right, so DeepMind and DNN Research, they went for 5 million and 400 million. So I mean, if a startup comes along and has a technology that is not infringing patents, it's definitely in the interest of these larger companies to gain a competitive advantage by acquiring them. But again, this happens pretty quickly. For example, with Hinton's company that he made at University of Toronto, he's now with Google, and we've speculated that since the amount of time between when he started that company and he was acquired, it was likely that this company was made for the sake of Google acquiring that technology. And this is all speculation.
Hey guys, great presentation. It's really informative. I apologize in advance if maybe you guys already spoke to this, but maybe I just wasn't listening, or yeah, maybe I just wasn't listening. But I was wondering, you guys mentioned as part of your forecast, you talked about emotion recognition. So I was wondering if you guys could maybe elaborate and explain its application or relevancy, because I'm pretty monotonous when I talk to Siri. It doesn't matter if I'm mad, sad, angry. I don't see how relevant it would be.
Like, are you asking me to explain how emotion recognition applies to speech recognition, or more like the potential applications?
I just don't, what is the value behind emotion recognition?
Well, because in speech, a lot of the stresses that we put on our words and the emotion that we put into the words has a lot to do with the meaning that we're trying to convey. And then so just Siri transcribing your words isn't enough to get the actual meaning of the word. So one purpose of speech emotion recognition is to be able to get the meaning behind the sentence, and not just the actual phoneme sort of processing. Did that sort of help?
Yeah, but I'm just, I guess maybe it's just because when I talk to Siri, I'm pretty monotonous, so I don't know how, I don't think people, if they're mad or if they're sad, that's going to necessarily translate when they're talking specifically to their smartphone and in voice recognition technology, because, I've been angry and I've wanted, Google Now to find something for me, but when, that anger doesn't translate when I'm talking to my phone. Do you know what I'm saying?
Well, just a second.
I just don't know how. I just don't know how, that. Okay,
What?
my question.
Yeah. Yeah, so one of the ideas behind emotion recognition is to have more natural human-computer interaction. So this is where emotion comes into play again. And one example that we came across during our research it's called Parkinson's Voice Initiative. And here they use voice recordings from people who are predicted or like expected to have Parkinson's, and they use a different speech database, and then they match the sort of emotions, not only the speech but also the way the tongue moves and then everything else, like the vocal tremors and the breathlessness and the weaknesses of the voice, in order to diagnose someone with Parkinson's, to screen someone with Parkinson's. So that's also like one possible application where emotion comes into play.
That's all I wanted to know, just how it applies outside of
So I just have a general question about applications. It's so funny. So I just have a general question about applications. I have two questions, really. The first one is quite simple. It's just, what are the military applications of this technology?
So one of the applications is, for example, in high-performance jets. If you're in a high-stress situation like a combat dogfight, for example, or you've got your hands full operating a joystick and a weapon selection control, you can actually extend the pilot's capabilities to go beyond just using his hands, because flying those high-performance jets actually takes a lot of mental concentration, and you don't always have enough hands to do what you need to do. And then another instance would be for recognizing fatigue, especially in pilots, because you're flying long missions on long hours, and you're less likely to actually come to your target if you're tired. So these feedback systems can actually give you warnings on when to rotate out your pilots, and they can actually give pilots feedback on if they've selected, let's say, the wrong munitions, or that they're arriving at the wrong target, or if they're flying erratically. And this can increase safety in the military and also potentially reduce incidences of wrong targets or wrong acquisitions.
That's great. So thank you for that. Do you have any insight into how it can be used specifically in the context of drone strikes by Reaper and Predator drones or intercontinental ballistic missiles? Can speech recognition be used to pilot a missile as it goes from, let's say, one region of the world into, the Swat Valley in Pakistan?
Hypothetically, it could, but that's not a very optimal method for actually guiding a missile.
No, I mean, instead of I meant instead of not guiding it with your voice, but instead of say, like obviously you can't say left at 20 kilometers per hour. That doesn't make any sense. I meant say instead of pressing a button, could you just say launch a missile at Pakistan from your house, like from your phone?
I mean, you could potentially do that, but based on how military procedure works, you would have a lot of fail-safes before you actually launch a strike or a missile like that.
Okay. So my second question relates to Rosetta Stone and learning through different languages. So do you know what kind of systems the Rosetta Stone and different language learning software use? Do they use deep neural networks or hidden Markov models, or what are they using?
We didn't actually look into Rosetta Stone, so we don't know.
Okay, thanks.
Hey guys, just a quick question, just from my own understanding. Neural networks, I'm just wondering what constitutes the nodes in the networks? Are they actual physical nodes or just clever programming?
So neural networks, it's all software. So it's not a physical node. It's just within that program. It's programmed to simulate what, like the neurons in the brain. So no, it's not a physical node. It's all within the software. But you have there's functions within that, such as a transfer function. For example, like this theoretical node in a neural network will still receive inputs, sum them up, and in the same way that a neuron fires, if these inputs reach that threshold function that's programmed into the node, it will then fire in a similar way.
Hi, thank you for your presentation. So with the software or product like Siri and Apple phones, it is used across the world, and different speakers or English speakers across the world might have different preferences of words, or they might have different accents. How is that overcome in these applications?
So we can only speculate to that question, but we think that given a specific speech corpus or a language model that that specific system is trained on, it should be able to be trained for that specific, I guess, vocabulary given that location.
So, for example, for English in like American English versus a British accent, will that require a separate training process and learning to be able to speak with different users?
That doesn't actually really require a separate process because it is based within the same language. What you can do is change out maybe some of the phonemes. For example, some of the accents that you may have on different words, like tomato versus tomato, you'd be able to pick that up based on the phonemes, and that's where they come in, because you can have, there are only a few phonemes that differ between American English and British English.
So will there be a mechanism in place required to actually detect of where the user is from, and in order to switch to a different mechanism of detecting that then?
You wouldn't really need a different mechanism because based on the language models and how the system can predict and infer meaning, it would still be able to predict those words based on like how it formulates the language model. So it's the same system, and it still picks up the same phonemes regardless of language.
Thank you.
I mean, regardless of origin, still in the same language.
Hey guys, so you were talking about forecasting, and several times you mentioned that your phone needs to be connected to the internet, and it sends all the information back to Apple servers or Google servers to do all the data processing. And then you guys discussed about the commercial, sort of the adoption. Do you think that the processing power of current technology doesn't allow for widespread commercial adoption? Because things like Apple servers and Watson and Deep Blue, that's not the kind of processing power, not even close to the kind of processing power you have on your phone.
So you are right. The processing power of something like a phone is not even close to being able to handle what's required for speech recognition. For example, Google uses 6 to 8 servers just to handle the requests. But there are incremental advances. For example, switching over from processing this using GPUs, it helps and makes this quicker. But I mean, with how easy it is to be connected to the internet, we don't really see this having too much of an effect on the ability for speech recognition technologies to become more integrated into, for example, your everyday life.
I know there's more questions, but I also want to say. Okay, so I think it's good to critically challenge something, and that's always very important. But what I want you guys to be careful of is I don't want you to engage in silo thinking. And so what you have to do, in my opinion, you have to bridge what you love to what's hot. So Jeff started by asking a great question, but I hope Jeff's not participating in silo thinking. Market capitalization. Actually, this question just came up this afternoon. I was on a call with several folks, and we were talking about market capitalization, so I had to look at this anyway. So top 5 companies in the U.S. by market capitalization, which de facto is the world for all intents and purposes. Number 1, Apple, then an oil company. Number 2, Microsoft. Or sorry, number 3, Microsoft, and number 4, Google. So that was in the first quarter. And in each quarter, for the past 3 quarters in 2014, the top 5 companies by market capitalization in the U.S. have been Google, Microsoft, and Apple. Now, your cherished pharma companies, for those of you who like to engage in tunnel vision and believe you can only do one thing in life. Well, let's see. How do they fare? Well, we have 3, but, you know, one of them's Johnson & Johnson, and Johnson & Johnson does medical devices, and for many of you, that's not really biotech. So now, of the top 10, by market capitalization in the world, we have 2 that are pharma companies out of 10. Okay? So, you know, when we're talking about this technology, this is really meant as a case study, and it won't stop here. This will grow in the program, just like everything else I introduce. The name of the game here is not just speech. The name of the game is pattern recognition. That's what we're after. Which brings us to Ted's comment, which is oh so appropriate. Okay, so, and that is, and I mean in a positive way. You know, I gave it to you in my spiel before, as I've given it to others, and I will repeat it at Sunnybrook in a couple of days. I see 2 key drivers for this: video games and drone warfare. And I'm not sure, maybe it was a member from the team, but someone sent me a tweet recently, which I retweeted. DARPA, the research military arm down in the U.S., they've just been testing artificial intelligence systems in small drones. And again, this comes back to the argument that a better drone is one that's more autonomous, which is another driver for speech recognition. So when you're thinking about this, you know, looking for valuation estimates on specific pattern recognition companies is a little like looking at valuation estimates for new cell lines in manufacturing and biologic. The bigger picture is possibly the biologic, or the bigger picture is the drug industry. In this context, the bigger picture is pattern recognition in the context of IT, which you're already using, right? When you detect spam and you have your spam filters on your laptops, that's making use of pattern recognition. Now, because we are engaging in forecasting here, and because this will be ever so surgically edited, I'll convey a speculation by a colleague and a friend of mine down at Harvard, who has been very unhappy with many of the changes taking place with Obamacare. He's a Republican, but he's coming around. And so we have vociferous arguments, okay? The sole reason we play video games together is just so we can argue. So anyway, here's his comment. It's a little conspiracy thinking, but it provides a sort of an intriguing context to this. He argues that the big push for electronic medical records in the U.S. is to facilitate the automation of diagnosing. And if we're going to automate diagnosing, we need advanced pattern recognitions to achieve that. And that'll be another major driver in the healthcare system. And he has an even more, a sort of a darker speculation on this, and that is the pattern recognition used in diagnosing doesn't have to be perfect. We're going to accept error. And the amount of error we'll accept will be based on the current cost pressures on our healthcare system. So pulling back, when you're thinking about this year, the team has done, you know, it's been no easy, they've been focusing on the technology rather than forecasting, but they've been doing basically speech recognition technology. Next year, I'll probably choose facial. And the idea here is not that the students come out of here and they're specifically familiar with the issues behind speech or facial, but you are now becoming conversant in the concepts of pattern recognition itself. And this really brings apart the whole general notion of, in a very general sense of the word, hacking. And all I mean by hacking, or the intended use of hacking as I understand it, is that you're sufficiently conversant in the technology so you know what's possible, so you know what to combine with what to create new product opportunities. All right, so we're talking about processing power. So again, if you're asking questions to have a spirited discussion, that's a good thing. But you know, when you begin to ask questions about processing power, I mean, really. So there's a few things that are certain for life, right? Death, taxes, and the cost and size of computation. So we know that's going down. That comes right back to speculating. What do you think is going to happen in the future? I think the smartphone is going to become thinner. I think we can all say that. I think we can all safely say, just as we can safely forecast there'll be continued unrest in the Middle East, we can also safely forecast that technology will continue to be miniaturized and drop in its price. So I wouldn't raise processing power here as an issue. That's sort of a red herring, a straw dummy. So in summary, you have to bridge between what you're passionate and the trends out there. That's what I've had to do. I'm a neuroscientist. How much neuroscience content in this program? Okay? Now you see the reality with the market capitalization statistics. If I were in your shoes, I'd be looking for a way, because I'd be looking for a way to cultivate options, cultivate employment options, cultivate career path options, so that when you go into the world, you just don't see yourself as a pharma person. Right? When you go into the world, you see yourself as being a little bit more flexible, being pegged to one industry segment. It's one of the few benefits I hope that you guys get when you're in here with us, is to be more open-minded when you look at different opportunities you can pursue in the world. Okay? Good questions tonight. I know we kept it short, and I'd like to thank our presenting team.